Today we're going to be talking about part of Lesson 10.3, specifically dealing with special right triangles. Our special right triangles are two triangles that we have that, just based on the angle measures that we have and what we know about trigonometry, we're able to develop these patterns that we can use to get these exact answers. And so the big key with this lesson is everything is going to be exact. We're not going to have any decimals or rounding or anything like that. We're going to only have exact answers. So let's go ahead and start to talk about our first triangle. Our first triangle we refer to as a 45-45-90. We don't usually call it that triangle. We usually call it an isosceles right triangle. Isosceles meaning I have two equal sides and then obviously a right triangle. Okay, in that theorem, and basically this is going to give us our pattern, it says that in an isosceles right triangle, the legs, or the two sides that are not the hypotenuse, you can think of it as the opposite and adjacent sides that we've been working with, are represented by x and the hypotenuse by x times the square root of 2, or x square root of 2. And so this can be a little bit confusing of where these things actually come from. This is what the theorem says. These are the parts that we have. But let's actually talk about where these things come from. So first of all, I have this triangle here. This is my 45-45-90. I have my two 45 angles and my 90. The two 45s, if you remember back to geometry, angles that are the same, their sides opposite them are also the same. So I know that these two sides are equal. Now what I'm going to do is I'm going to call each of these sides simply x. I don't know what the sides are. I just know that they're the same, so I'm going to use the same variable to represent them. Well, based on that, we can actually find the third side based on whatever this variable is. So if we do that, we're going to use Pythag. So I'm going to square those two sides, and I'm going to say that it's equal to c squared, and I'm really referring to this other side here as c. Well, I can now solve for c. I have x squared and x squared. That gives me a 2x squared is equal to c squared. Now to get c by itself, I need to take a square root. And when I take the square root here, this on the c here, I get just c. The squared and the square root cancel. The same thing happens on x. When I take the square root of an x squared, I get just x. The tricky part here is the 2. I cannot take a square root of 2 and get an even number, okay, or a nice kind of whole number. I get this crazy decimal that goes on. It doesn't really repeat. It's just a number. So what I'm going to do is I'm just going to simply leave it as a square root of 2. Now these are being multiplied. There is one little trick that we do. We do put the x on the front, and that's just so that we know that this x is now outside of the square root, because I've already done that piece. So I put the x on the front, and now I have that x squared of 2, the same piece that I had here, which finishes out my pattern. Alright, we're just going to talk about these patterns for now. We'll talk about how we use them here in just a little bit. Let's talk about the other one though. The other one that we have is our 30-60-90 triangle, which again refers to our angles. This one we do just refer to as 30-60-90. So I have 30 degrees, 60 degrees, and then my right angle, which is the 90 degrees. In this one, we get a slightly different pattern, and we'll talk about again where that comes from in a second. But in a 30-60-90 triangle, let's get our pattern written out here. The shortest leg, or the shortest side, is x. The other leg, or the longer leg, is x square root of 3. And the hypotenuse is 2x. Okay, so again, I get this pattern, but we should probably talk about where these pieces actually come from. So again, you don't necessarily need to know or be able to replicate where these patterns come from, but you do need to know the patterns and how to use them. But it makes a little more sense if we know where they come from. So this 30-60-90 triangle is actually part of a bigger triangle. It's what we refer to as an equilateral triangle. In that equilateral triangle, all of my angles are equal and all of my sides are equal. Okay, the problem is in that triangle I don't have a 90-degree angle. So what we've done is we've taken this triangle and I've split it straight down the middle. By doing that, I've done two things. I've kept this side on the outside as a full side, and I've taken the side kind of on the other piece of it, and I've now split that whole side in half. So if I want to call this small side x, that means my full side is 2 times that, or 2x. But that goes the other way as well. If I call this 2x, then half of it is the x. So I'm going to go ahead and fill in those two pieces right now, 2x and x. Okay, and I do now have my 90-degree angle here. Excuse me, if I look at my other angles as well, I have a 60-degree angle because in an equilateral triangle they're always 60, and I have split my other 60-degree in half, so I get a 30. So I have my 30, my 60, and my 90. So what I'm looking at now is this, triangle that's actually printed on your page here. And we can start to try and find this third side. So this third side is my longer leg. Remember, legs refer to the two sides that form the 90-degree angle. It's the two sides that are not the hypotenuse. Hypotenuse is across the 90. So I'm really trying to find this longer leg, or the kind of the middle side as far as length. So to do that, I'm going to set up another Pythag problem. Okay, now this one, I don't know this side, so I'm going to refer to it as A. And I'm going to take x squared, and I'm going to add it to a squared. So a squared plus x squared is going to equal my hypotenuse squared, which is 2x. I'm going to throw that in parentheses and square. I'm putting parentheses because I'm squaring the entire thing, not just the x, not just the 2, the entire thing. Okay. To start here, there's not much I can do on the left-hand side, so we're just going to bring that down. But I can start to simplify the right-hand side here. Now, 2x squared, the 2x is being squared, so it's 2x times 2x. Well, there I can multiply the 2's together, which gives me 4. And x times x gives me an x squared. Or here I'm really squaring the 2 and the x separately. So 4x squared. Now I'm going to combine my x's, so I'm going to subtract an x squared over to the other side, which gives me a squared is equal to 3x squared. Then I'll take my square root to get a by itself. When I do that, I have the same thing that I had up top here, which is I can take the square root of the x, but I cannot take the square root of, up here it was a 2, now it's a 3, so I'm going to leave that. Now in this case, I'm just going to throw the x to the front right away, and then put the 3. So now I'm seeing here that my last side is x square root of 3, which is what I said based on my theorem. Okay, so you can start to see where these patterns start to come from. It's really just a lot of Pythag and kind of knowing the relationships within those triangles to begin with. Now the nice thing is once we know those patterns, we can use those patterns in triangles that have some pieces filled in but not all of them. And so that's what we're going to do as we start to get into our examples here. Our first two examples, A and B, for number 1 here, are referring to our isosceles triangle. And the way I know that is I have these 45-degree angles. So I'm going to fit my pattern to this right now. So what I know is I know that my two sides that are forming my 90 degrees are going to be equal to x. And that's just from the pattern that I have. And then my hypotenuse is going to equal x square root of 2. Well, now this simply just becomes a replacement sort of a game where I have this x. Wherever I see x, I can plug in that 7. So if I go to b here, well, b is equal to x, and x is equal to 7, so then b must be 7. And I can do the same thing in a. Now, this one's a little bit trickier because I'm plugging the 7 in for just the x, but that square root of 2 is still there. So I replace the x with the 7, and now I have that a is equal to 7 square roots of 2. Now, this is that really important part that we're looking for exact answers, which means I'm not going to round. I could grab my calculator right now and type in 7 times the square root of 2 and get whatever that decimal is. I don't care what that decimal is, though. I want to know the fact that this is 7 times the square root of 2. That actually tells me more right now than the decimal that I have. Okay, so we want to make sure we're leaving those square roots as part of our answers. That's what we mean by exact answers, is no decimals, leave the square roots. Now let's go to part B. For part B, we have the same type of triangle, my same isosceles triangle, but now I have pieces that are in different spots. What I mean by that is I have x here, okay? That's part of my pattern, so I'm just going to leave it. Y here is the other x, so I know that y is actually equal x, the same x I have here. So my two answers are going to be the same. The problem is I don't know what they are yet. What I do also know is that this 4 up here is in the hypotenuse. Now the hypotenuse has the pattern of x square root of 2. So if I'm trying to find my values for x and y, which are going to be both equal to x, then I need to take this equation that I just wrote here, and I need to solve it for x. So what I need to do is get x by itself. Now, I'm going to bring this down to the bottom here. I have x square root of 2 is equal to 4. Now, in order to get x by itself there, I need to divide by the square root of 2, which I'm allowed to do. The square root of 2 is just a number. Okay, it's just like a dividing by a regular 2, but I have to keep the square root on it. By doing that, I get x is equal to 4 over the square root of 2, which seems like a perfectly fine answer. However, mathematicians for a long, long time have decided that we are not allowed to leave square roots in the bottoms of fractions. It's kind of like reducing a fraction, that we always need to reduce those fractions. Same idea. It's what we call convention. It's just what we've decided we want to do. So we have to follow that. So now we have to talk about a process called rationalizing the denominator. Write that out here. Rationalizing the denominator. Okay. What we mean by that is we need to get the square root out of the bottom. Okay, and we actually did this a little bit when we talked about complex numbers. When we had i's in the bottom of fractions, we kind of got rid of that. The way we did it is we multiplied by whatever in the bottom on both top and bottom. And what we're doing there is I have a fraction that's the same on top and bottom, which means it's equal to 1. I could reduce that to a 1. I'm not, because I want that part. Okay, but this is really equal to 1. And I'm multiplying by 1. Multiplying by 1 doesn't change the value at all. All it's going to do is change what this looks like. Okay, so by doing this, I'm not changing the value, I'm just changing what it looks like, and I'm trying to get the square root out of the bottom. Now, if I multiply, I go straight across, so this is 4 times the square root of 2. There's not much I can do with that, so we'll just leave that there. And now I'm dividing by a square root of 2 times the square root of 2. Well, that's multiplying the same thing by itself, which we could rewrite as that square root of 2 squared. Simply multiplying the same thing by itself is the same as raising it to the second power. Let's zoom in a little bit here so you can see that. So I'm squaring that square root. Now if I square a square root, those cancel, and I'm simply left with a 2 on the bottom, and I have 4 square roots of 2 on the top. The last thing I can do here is I can look to see if I can divide these. Now, sometimes I can, sometimes I cannot. If I cannot, I would leave my answer like this, because that's my exact answer. But here, I can do 4 divided by 2, so I'm going to go ahead and do that. 4 divided by 2 is 2, and then I keep the square root of 2. The important thing here is that that square root of 2 is still there. I cannot simplify anything with that, because that square root is there, it kind of locks it in. So I can't divide that by 2 or anything like that. So I keep it as 2 square root of 2. Now that is my value of x. If I follow all my equal signs backwards there, that is x. So that is my value here for x, and we've already said a couple times now that x is the same as y, so I get that same 2 square roots of 2 for y as well. So those are exact answers, again, leaving those square roots as part of our answer. Finally here, going to number 2. Okay, number 2, again, I'm talking about my exact values. The only difference here is if you look at your triangles, we're going to have some different triangles. Okay, these triangles are referring to our 30, 60, 90s. Now, since I'm on a new page, I'm going to take some space down here on the bottom and just kind of draw my 30, 60, 90 triangle that we have on the front, just so we have it kind of for reference here. So my 30 is down here, that's my small angle, 60 and 90. Across from 30 is x, across from 90 is 2x, and across from 60 is x squared root of 3. And you can go back and verify from that from the front page as well. If I go ahead and start with A here, though, I need to start to identify what information I know and where my pattern sits in reference to what I have. So we have to go based on the angles that we know. So I know I have 30 degrees. If I look at my pattern, across from my 30 degrees is x. So across from my 30 here is the 2. So I'm going to call that x. Okay, across from my 90 is my longest side. That's my 2x. And across from the 60, which is my other angle up here, is going to be the x squared root of 3. So that's my side along the bottom here. Okay? Essentially what I'm doing with my pattern is I've just flipped this triangle over to the other side. So now let's start to fill in that information we know. I know x is equal to 2, which means if I go to u here, I can plug a 2 in for that x. If I do that, this becomes 2 times 2, which I can simplify to 4. So u needs to be 4. V is going to be very similar to what we did on the front side. I can plug the 2 in for the x that's there. The square root of 3 is just going to stay. So I have 2 times the square root of 3. And there's my answer. Part B is going to be a little bit trickier. Okay, again, I'm going to set up my pattern first. So I have my 60. My other angle up here is going to be my 30. I'm going to do some weird things here just because of the letters. I'm going to switch these letters real quick. Let's call this A and B, which makes this A and b. The reason I'm doing that is I want to use x just to fit our pattern. You could, I guess, use a different letter in the pattern as well, but we try to stick to that x. So across from the 30 is our x, across from the 90 is our 2x, and across from the 60 is our x square root of 3, just filling in our pattern that we have. Now, what I need to do is I need to use the one that I actually know, which is across from my 60 here, the x square root of 3 is 5 square roots of 3. Now, this one's going to work out a little bit differently. I need to get x by itself, so just like before, I'm going to divide by the square root of 3. Now, this one's going to work a little bit differently, though, because my square roots of 3 cancel on the right, and they actually cancel here on the left as well, which means now that 5 is equal to x. Okay, now that doesn't mean that this side changed value. This side is still 5 square roots of 3. But when I start to look for my pattern, that x value is going to be 5. So my b down here is 5, and my a is going to be 2 times 5, which is 10. Okay, so what I just figured out now is that a here is 10, and b is 5. Okay, now one really important point here is the only reason this happened is because I had the square root on both sides, so when I divided, those canceled out. If this was just 5 here, and I didn't have the square root, I would now be in the case where I need to rationalize my denominator again and multiply by the square root of 3 on top and bottom, similar to what I did on the bottom of the first page here. So this process that we did for 1b could have very easily happened for 2b here as well. The only reason it didn't is because I have that square root. Okay, so just be careful. You may have to do that for some of these as well. Okay, that is it for our video for today. If you have any questions, feel free to reach out and ask me either by email or talking to me, and we'll get those questions answered for you.